All right. Well, thank you everyone for attending this course. Welcome to the Introduction to OpenFOAM course. My name is Björn Windén. I'm with High Performance Research Computing at Texas A&M University. This is a kind of agenda for today's course, even though this is a mostly hands-on, logging into the cluster, typing the commands kind of course. I will spend a little bit of time in the beginning talking about a little bit of background. What is OpenFOAM? What isn't OpenFOAM? And how is it kind of different from other CFD packages? And a little bit about basic structure and things like that. I want to do this before we dive into the hands-on session, just so people have a little bit of a perspective. I find that it's easier to get used to the environment if you know a little bit about the background. And with regards to the hands-on session, we're going to be logging into ACES, and I'm going to walk you through how to do that. We're going to run a basic OpenFOAM tutorial. Usually these tutorials are kind of self-running. You don't really have to do anything. You just press the button and they go. But we're going to do it step by step manually, just so we get a grip on what's going on and what we're doing. We're going to do some post-processing with Paraview. And then we're going to go in the second half, we're going to go into a little bit more customizing, modifying things to suit your needs, and running in parallel, and stuff like that. And we're going to end with a Q&A. I will say the last point, implementing new methods, we'll do that if we have time, meaning we'll do the hands-on bit if we have time, but I will always leave the instructions for how to do it, how I would have done it if we had time, so you can do it yourself in your own time. But it's not, there's no magic going on, so you should be able to follow those easy commands on your own. Okay, so very quickly about me. I'm currently a professor of ocean engineering, but I'm also faculty liaison here at High Performance Research Computing. My research is about ship hydrodynamics, which involves like high Reynolds number flows, 1 million to 10 billion Reynolds number, multi-phase, a lot of complex stuff like propeller, rudder, hull interaction. I started using OpenFOAM a while back in 2010. Back then it was OpenFOAM version 1.7. Between then and now, it's gone through quite a journey. So OpenFOAM now isn't quite what it was back then, but we'll talk a little bit more about that. So what is OpenFOAM? First of all, it has nothing to do with foam. FOAM stands for Field Operation and Manipulation. So it's basically a library. Originally, it was a library to perform field operations, meaning solving partial differential equations for fields like velocity fields, magnetic fields, what have you. It started as the foam library for fluid and solid mechanics in the 90s in Imperial College London. They based it on C++ rather than Fortran, which was kind of the go-to thing back then. The benefit of going with C++ over Fortran is it's very modular and easily expandable. So that's kind of contributed to a lot of the success behind OpenFOAM. It was so successful that they released it under the new public license in 2004 and called it OpenFOAM. And since then, it's been completely open source and usable by anyone who wants to have a go. Now, 20 years later, it's kind of a huge community-driven toolbox of various types of methods, but the core is still this field operation and manipulation library, meaning linear equation solvers for partial differential equations. So that's mainly used for CFD, but there are other applications as well that benefit from matrix solvers. OpenFOAM isn't one program. There are many different development tracks, both commercial and open source. But all of them have in common that they run in a Unix-like environment, either Linux or Mac, or a Windows environment emulating a Linux or Unix environment. We will talk a little bit more about that as well later. So here's a kind of open overview of what OpenFOAM is today. We have on the left, we have OpenFOAM version one number, meaning version 1, 2, 3, 4, 5, 6. It's now up to OpenFOAM 11. That's run by the OpenFOAM Foundation. That was the original kind of originator of OpenFOAM. It's also spun off into a commercial track by OpenCFD. It's still open source, but they have a commercial spin on it, so they offer various types of training and support and stuff like that. That version is called version and then year and month. The latest one is version 2023-12. There's also Foam Extend, which is a kind of a community project led by the original Foam developers. I guess they felt that the kind of structure that came with the official releases hindered them a little bit from testing new experimental methods and having the community contribute. So Foam Extend has a lot of community-made tools and solvers and stuff like that. And by extension, it may be it's experimental and therefore slightly possibly unstable. But if you're looking for new methods, Foam Extend is definitely a great resource. Then there are a lot of others. People develop their own kind of in-house forks of OpenFOAM. It is open source, so anyone can take it, copy it, and make it their own. I just took a few examples from my field of ship hydrodynamics. The US Navy has their own kind of development of OpenFOAM that they call Navy Foam. There's a shortcut package for ship hydrodynamics and a bunch more. One that I wanted to point to is one called Blue CFD, which is basically an emulator of a Unix environment for Windows. So that will run in Windows. So it's a good, if you're kind of not sure if you want to take the plunge and install a new operating system to run OpenFOAM, you can kind of test it out in Blue CFD, and it runs fairly well. I will say though that it will be slower than if you run it native on a Unix machine. And all of these different versions are mostly the same. I would say they are like 90% the same, but each different version has different quirks and depending on what people work on developing them, they introduce slightly different methods and slightly different ways of solving various problems. So you kind of have to search a little bit what's currently being used for what the problem that you are interested in. Today, we're going to be using the far left one, OpenFOAM version 10. We're not going to use 11 because it's not available on the cluster quite yet. It's very new. So how is OpenFOAM different? I like to use this kind of picture of a comparison with a commercial solver. When you purchase a commercial CFD package, you purchase kind of a well-oiled working machine, and you get a GUI of various controls that lets you control that machine, and you push the button and out comes a result. And it might be slightly hard to know what goes underneath the hood. OpenFOAM, on the other hand, is basically a big pile of parts and components and a toolbox, and allows you to put together a solution that works for you manually. Now, this seems a little bit daunting. When I buy a new car, I don't want to buy it in pieces. Fortunately, there are a lot of pre-assembled tutorials, both that comes with OpenFOAM as you download it, but also that you can download online. Other people have assembled. So kind of positives with commercial solvers that they're easier to learn. There's support available when you purchase them. The solvers are more stable, and they're controlled from a familiar environment, Windows GUI. On the negative side, they are expensive, especially if you're interested in high performance computing, because you usually pay per core. And if you have a problem that requires hundreds or thousands of cores to solve, then that's going to cost you. They can be customized, but they're not as easy to customize as OpenFOAM. And I said there's a plus that solvers are more stable. That can also be a minus in my view, because when people buy a CFD software, they're expecting results to come out of it. So the solvers can sometimes be a little bit too generous with bad user input to generate a result, which is not good if you are. That's good if you are on the clock and want to produce something to show a client, but maybe not so good if you're actually interested in accurately resolving the problem and studying it in detail. It may take a little bit longer for new methods to be implemented in commercial packages as well, because they have to go through fairly rigorous Q&A quality control, in order to be released. OpenFOAM, on the other hand, you can customize it any way you want. It's free, regardless how many cores you use. If you can get your hands on a machine that has 1 million cores, you can use OpenFOAM for the same costs as 1 core, which is 0. It also has an active user community, especially in academia. So a lot of pre-made setups and also user-made solvers and stuff like that can be downloaded online. On the negative side, steep learning curve. Hopefully this course might be one step to overcoming that, but we'll see. Again, solvers might be more unforgiving. That doesn't mean that they're badly designed. That just means that they don't have what commercial solvers often have, is artificial stabilization of the solver. So whereas in OpenFOAM you have garbage in, garbage out, sometimes in commercial solvers you can have garbage in, pretty pictures out. But that can be frustrating for sure. And also you don't need to, but to take full advantage of what OpenFOAM is, you need knowledge of C++ programming and scripting. So quickly, just an overview of what the structure of an OpenFOAM case is. Say you have OpenFOAM installed somewhere on your computer or on your cluster environment. That means that in that location we have all of these tools and all of these components stored. And then when you want to actually use them, you create a case somewhere in your own environment. If you're on your workstation, maybe in a home directory. If you're on the cluster, maybe in the Scratch directory, where you put little files that tell OpenFOAM what parts to pick out from this big pile of tools. And you can modify those files. So you can say you can tell the whatever solver you're using. You can tell it to pick out a specific turbulence model. You can tell it to pick out convection schemes, etc. So when you run the OpenFOAM commands, and we're gonna do this hands-on in a little while, so don't worry. It will look through those settings files and it will pick out those tools and those components from the OpenFOAM installed location. This is basically what I just said. One point to make here is that there is a file called the bashrc that comes with each OpenFOAM installation that you have to source. And that's going to tell the terminal that you're currently in where to find all the components. So it's very important that that file is sourced, but I'll show you how to do that. And as I said, when you run OpenFOAM cases, you usually store them under your own profile somewhere. Home directory if you're on your own machine, or Scratch directory if you're on the cluster. So this is the basic structure of an OpenFOAM case. We have a folder, which can be called anything. In pretty much every OpenFOAM case, we have 3 basic folders. We have one called system, which contains the main settings controlling the solver. We have a start, end time, what's the time step, what numerical methods are we using, what numerical schemes are we using, and what settings are we using for mesh refinement. And then we have a folder called constant for things that are constant, like physical properties, environmental constants, a value of the gravitational acceleration, density, etc., and the turbulence model. The mesh is also there. The mesh is not necessarily constant, but it is in the constant folder. And then we have a folder called 0. So the case, when you run it, it will have a lot of folders with numbers, 0, 1, 2, 3, 4, 5. Those are basically the time step data for the case. The 0 value is usually there from the start, because that contains the boundary conditions. So the boundary conditions will be copied to subsequent folders like 0, 1, 2, 3, 4, 5. But the 0, 1 is there to give the initial conditions and the boundary conditions in the same place. So what we need to take away from that is 0 contains boundary conditions and initial conditions. Okay, as I said before, when you download OpenFOAM or when you load OpenFOAM on the cluster, it contains a lot of tutorials. Each tutorial comes with a script called allrun that contains all the commands you require to run that tutorial in sequence. So you basically just have to run it, and the tutorial runs, and then you're finished. But that's a little bit cheating, and it's not very educational. So for today, we're going to do a tutorial, but we're going to not use the allrun script. We're going to manually run all the commands and discuss what they do. So let's go over to the hands-on session. So I'm going to close this. Okay, so I am now at the HPRC website, hprc.tamu.edu. One thing I want to show first, you should have all gotten a link to this page with the course invitation, or the course email you got earlier today, I believe. Click here, training. It will come up with a menu that will say short courses. And at the bottom of that, oh, there we go. Oh, okay, there we go. Short courses, and at the bottom there's introduction to OpenFOAM. If you click view details here, there is a document here called instructions for OpenFOAM tutorial. So that's basically every single command and every single action that we will do today as part of this tutorial. If you want, please go ahead and open it and keep it so you can run it by yourself after this course is finished. But also during the course, you will be able to copy and paste commands from this document to the terminal. So okay, let's see if this works. So in order for us to log into the cluster, to ACES, we're going to go to portal, and that works quite. There we go. And then don't click the portal button, but just hover over it and move down to the ACES portal. Here we go. Now I'm already logged in, so maybe I'll log out so it's a little bit easier. I'll log out from everything. Let's see again if I get to the login page. No, okay. Well, when you click the ACES portal, if you are not logged in like I am, it should bring up a prompt that asks you to log in with your access ID or your institution credentials. Please follow that. And I'm going to leave a few minutes for people to get to this screen, and let me know if people have problems getting to this screen. So there are a bunch of things you can do here. You can access the cluster directly. A shell access is through there. We're going to do today's tutorial through a VNC session. The reason I want to do that is I want to be able to run Paraview together with OpenFOAM. OpenFOAM doesn't really require any graphical user interface to run, but if you want to be able to look at what you are doing, we want to have Paraview open as well in the background. So I want to do this through a VNC session, and I still can't click that one, but it's under interactive apps. And you can see that there is a VNC OpenFOAM short course right there. And we're going to click that. This should open up a little menu here. So you can choose. We're going to choose CPU only. We're going to do, I'm going to say 3 hours. I'm going to assume we don't overrun by too much. But important thing here is we're going to ask for 3 cores. That way we can do some parallel processing. And we're going to ask for 5 GB of memory. I would recommend starting with font size small, otherwise it kind of breaks and fills up the whole screen. We can change that later. And then we go. The reason that we have a special one here called OpenFOAM short course is because we made a reservation for the resources. Normally, if you're not part of this course and you want to log in, you just type VNC. You select the VNC. And it's going to work exactly the same, except if you ask for a lot of resources, it's going to make you wait. But this one hopefully shouldn't make you wait because we reserved it. So I click launch. Okay, there we go. I'm going to launch it. Just changing the font size here so it's easier to read. I think that might be a good size. Okay. As I said, if you are behind on anything and something doesn't work, all of these steps and commands are available in that document that I just showed you. So you can just go in and look at it afterwards. So the first thing I want to do is I want to minimize this original terminal, which I can't do because my mouse doesn't work. But I'll start a new one by right-clicking in the background and clicking Xterm. Gives me a new terminal. This is the one I'm going to use for OpenFOAM. I'm going to see if I can rename it. I can't. Okay. And then I'm going to open another one, which I'm going to use for Paraview. Normally, I would try to minimize the first one, but I can't seem to do that. Maybe if I do that. Oh, okay. Anyways. And okay. So if we are in one of these terminals, the first thing we want to do is want to load OpenFOAM. Now, this normally involves quite a lot of typing and checking which modules are dependent on which. So I made a little script that kind of simplifies the typing here. The script is available on ACES, so you can use these commands on ACES. If you want to do this in another environment, I also included in the instructions document the actual commands that are that script runs. So you can do it in any environment, but we're going to start by doing source/scratch/training/OpenFOAM/OF functions. OFFCNS. Do that. Now that has loaded some helper functions for this course. And the first one I want to use is I want to load OpenFOAM. So I do load OF10. And there is going to be a little error there. We can ignore that. I noticed that the other day, but it doesn't seem to have an effect on the actual function of OpenFOAM. So don't worry if you have get that error. The second thing we want to do is we want to create a directory somewhere that you have access to, where we can run our OpenFOAM cases. So we do make dir, and we want to do it in Scratch. and we're going to call it foam run. So I already have that directory already exists for me. That's why it complains, but for you, it should work. And then we change to that directory. We are now in that directory. Okay. The next thing we want to do is if we can access this terminal. Now I've loaded OpenFOAM in this lower terminal. I want to load Paraview in this upper terminal. I'm loading them in different terminals just so that they don't interact too much with each other, which may be a problem on the cluster. If you are on your own workstation, usually you would be able to load them in the same terminal because you would have installed them at the same time. But in the cluster, we have a lot of different versions and a lot of different libraries, so it's safer to load them in separate terminals, so we make sure we don't have any conflicts. So again, we want to see if we can actually type in this terminal. So I might start a new one and see if that works better. Yeah. So I'm gonna source that functions file again. source/scratch/training/OpenFOAM/OpenFOAM functions. And then I'm gonna load PV11, which loads Paraview. Again, if you want to see what the actual commands are behind there that I was too lazy to type, they are in the instructions document. So we got Paraview loaded in this terminal now. So we're going to leave that for a little bit and we'll come back to it when we need it. Let's go back to this terminal where we loaded OpenFOAM. So now we're going to run a tutorial. I picked the wind around buildings case because it's a fairly simple case, quick to run, but it still uses quite a few of the features that we might be interested in. So we have another custom command at our disposal here because we loaded that OpenFOAM functions earlier, which is called copy foam tutorial. And we're going to copy the one called wind around buildings. Be sure to pay attention to the uppercase and lowercase letters here because it is sensitive to that. So it copies it. I already had it, so it asks if I want to overwrite. I do, so I picked yes, but it should not ask you that if you don't have it already. And now we cd to wind around buildings. Okay, so we are ready to start. Do we have any issues getting this far? No? Okay. I saw there was some issues with accessing ACES. Again, if you fall behind a little bit, don't worry. All the commands and everything I do is in the instructions document. I will make a little bit of pauses like this to allow people to catch up. Okay, so we're going to run the wind around buildings tutorial. First thing I want to see is I want to type ls and see what's in this tutorial. So as we talked about before, we have 3 folders, the 0, constant, and system folders. And we also have this all run script that I said all tutorials have. We also have an all clean script that kind of cleans up. If you want to restart and want a clean start, you can run that script. Let's see what is in the actual all run script. So it has a few commands. This top bit here just loads some of the OpenFOAM functionality, so we don't have to worry about that. But we have these commands here: surface features, block mesh, snappy hex mesh. And then when it says run application, get application here, that means it gets whatever application is stated in the control dict, which is a file we will look at shortly. So I want to spend a little while before we start actually running it to go through what is in these folders, because when we looked at the slides before, I just showed like a graphical overview of what the folders look like. I want to see if we can look a little bit what's inside them. So if we start with for example, the system folder, you don't have to follow these files. You can just look at my screen. We're not gonna change them at this point. I just want to bring them up so we can look at them. See if I can make this a bit bigger. Okay, so this is the control dict in the systems folder. It's basically the most high level file that there is in OpenFOAM. It controls things like where to start from. We see here that it says latest time. So if you already ran a simulation and it stopped and you want to continue it, it will start from whatever the latest time is. You can also say start time here, and start time is 0. So it will also always start from 0. You can control things like the time step, write interval, and stuff like that. So that's the control dict. We also have a file called FV solution. FV in this case stands for finite volume, because this will be a finite volume calculations. So we see here that you can specify, for example, for pressure, what is going to be the linear matrix solver to solve the equation for pressure. We see here we have selected generic algebraic multigrid. You can type anything you want here. Obviously, you have to type something that exists, but this is, everything here is fully modifiable. So you can go into this file and kind of modify it to your liking. I should say that for most of the time, like 90% of these files, when you get a tutorial, if it's close enough to the application that you are interested, you wouldn't change it. So most of these things would stay the same if your tutorial is kind of close to what you actually want to do. And then we have a little dictionary here for the simple algorithm. We have residual control. This means that it can automatically stop the simulation if it detects that the residuals are below a certain value. In this case, for pressure, velocity, and the turbulent quantities, 10 to the minus 4. And then we have some relaxation factors here. You can set relaxation factors for pressure and velocity, etc. We've set them to 0.3 and 0.7. Respectively. So that's the FV solution. If you will remember here that I select the solver GAMG, and for U, K, omega, and epsilon, I selected the smooth solver. If you remember that, you will see later when we actually start the solver that it will tell you that it picked these particular solvers from this file. Okay, we're going to look at another file called FV schemes. Again, FV stands for finite volume. So these are numerical schemes in the finite volume method. We have schemes for time marching. In this case, this tutorial is steady RANs. So the time marching scheme is just steady state, nothing. We have schemes for gradients of various values. In this case, it's a cell-limited Gauss linear gradient. We have schemes for divergence. Again, we see here for U, we've got a linear upwind scheme. And for turbulent quantities, we have a limited linear scheme, which is kind of a blend between a central differencing and an upwinding scheme. So that's the FV schemes. Again, if the tutorial is close to what you want to simulate, usually you don't need to change much here. What else do we want to look at? Maybe we'll take a look at something in the constant directory. We'll take a look at the physical properties file. Here, as you can see, it just says new. The kinematic viscosity is 1.5 to 10 to the minus 5. These numbers in front of them, I should explain, is OpenFOAM has a way to check that the dimension of all the variables they use is correct. So this vector is basically a way to dimensionalize a constant, and each one of these elements of the vector represents an SI unit. So we got like length, we got weight, we got time, we got etc. So if you know what the dimension of kinematic viscosity is, you can work out which one is which from this. Okay, we're gonna take a look at one last file, I think, in the 0 directory, U, for example. So as I said, this will, when you start the simulation, you will get more files that are not called 0, but that are called 1, 2, 3, 4, 5, depending on how often you save your data, and that will contain the velocity. Basically, we can see right now at the start, the internal field is a uniform 0, 0, 0 velocity everywhere. But we can also see that we have some boundary conditions here. We have inlet. We have a fixed value of U inlet, and U inlet is described up here. So we have a fixed value of 10 meters per second in the positive X direction at the inlet. And at the outlet, we have this pressure inlet outlet velocity, which is basically an adaptive condition on the outlet. I should say OpenFOAM has all these funny names. Usually they're rather descriptive, but there's no way for you to guess what your options are here to put. There are some, you can Google it, but it varies in definition from different versions. One trick that I was taught very early on, and that I've used very extensively, is if you want to find out, for example, what kind of outlet boundary conditions are compatible with this simulation and this setup that I have at the moment, you can just type some gibberish here and then start the simulation, because it will throw an error and say, I don't know what the boundary conditions is, but these are the available ones that are compatible with this setup. So that's a great way to kind of, and then they will still have funny names, so you might not know exactly what they do, but then at least you can copy those names and Google what they do, or you can go into the source code and look for yourself what they do. Okay, we're gonna keep the one that we had. Okay, so now we kind of looked a little bit at the settings. Now we want to go ahead and generate the mesh. So we go into, you don't need to do this, but I'm going to show you what it uses to generate the mesh. We have something called the block mesh dict. So OpenFOAM has two major mesh generators. One is block mesh, which does what it says on the tin. It generates a block with a mesh in it. So very simple, and it's not super useful unless you have a very simple geometry. You can bend and warp the blocks to bend around airfoils and stuff like that, so it can be useful for that. But any kind of arbitrary geometry, this is not very useful. For that, we have the OpenFOAM mesher called Snappy Hex Mesh. But Snappy Hex Mesh requires a kind of a background mesh. So that way we always still have to use block mesh. So in block mesh, we basically define vertices X, Y, and Z. And then from those vertices, we define blocks. If you're interested in the kind of how to do this, there are some pretty good tutorials online. You know, what the order of the vertices should be in order to define a block. You know, each a hexagonal or a block should have 8 vertices. But what order they go in determines what's the main, what will be the orientation of the main coordinates system and stuff like that. And it is possible to define blocks inside out and in all sorts of weird ways that are going to give you trouble. So if you want to know how to do it properly, there's good tutorials in the OpenFOAM user guide how to do that. But this is a tutorial, so it's already been set up for us. I want to mention here that in BlockMeshDict, you can also define the boundary types and the extent of the boundaries. So basically, this means that I want the inlet to be spanned by these 4 points. These 4 points create a patch, which we call inlet. So that allows us to later apply boundary conditions to that patch. But again, if you just want to run the tutorial, you don't have to worry about this, but you probably need to go in and modify it if you want to modify the tutorial. So I wanted to show you what it looks like. Okay, so we are ready to run the block mesh. So we're going to run block mesh. I'm going to see if I can make this a bit bigger so we can see what happened. So it generated the mesh. It created 6,000 points, 5,000 cells, and it created this bounding box based on the numbers that we gave in the BlockMeshDict. So the next step, as I said, we want to do a simulation of wind around buildings. So this mesh obviously does not contain any buildings. So we want to go ahead and add those, and we do that with Snappy Hex Mesh, and that's controlled with a dictionary called Snappy Hex Mesh Dict. Snappy Hex Mesh has basically 3 main stages: castellated mesh, snapping, and add layers. I'm going to see if I can change the screen share quickly so I can show you what those are. Just give me 1 second. This is kind of hard to explain with words. Okay, so this is, so you can see here, the gray bit here is the uniform block mesh that we had. What we do is if we have a CAD surface, OpenFOAM usually works with stereolithography STL files. If we have a CAD surface that intersects this background mesh, it will basically split the mesh at that intersection to refine it around the surface. And it will create, and then it will delete anything that's inside the surface. So, and you have to define, it could either delete anything that's inside the surface like this to create the outline of a car, or if you're meshing, for example, a pipe or whatever, you can delete everything that's outside of the surface. So you have to define a point what's inside and outside. Anyway, in this case, we say we want to delete everything that's inside, and then you get this kind of jagged mesh that looks a little bit like Lego, and that's the first step. That's the castellated mesh. The second step is to snap all the vertices to fit to the surface, so we don't have this jagged mess. So that's the snap, hence the name Snappy Hex Mesh. Then there's a third step of adding prism layers, growing them out from the surface in order to resolve the boundary layer. But that's not part of this tutorial, so we're going to skip that from now. And I should say one unique thing about Snappy Hex Mesh, in all of these steps, it continuously monitors the quality of the mesh. So it won't proceed with the next step unless it's satisfied that the quality is good. And if the quality is not good, it makes adjustments. It maybe coarsens it or refines it slightly in order to reach an acceptable quality. So that's kind of a unique thing with Snappy Hex Mesh. Okay, I'm going to see if I can go back to the terminal again, which is here. Okay. So I'm gonna close. We're gonna look at this. So in the castellated mesh controls, as I said, it has a surface that it kind of overlays on the background mesh. In this case, we have something called buildings.obj. So it's an object file, but this could be an STL file or any other CAD file format that OpenFOAM supports. And then we have a refinement box, which is just a box that we define around the buildings that we can add extra refinement in. So in this geometry, this doesn't specify anything to do with refining per se. It specifies geometry. So we say that we have buildings here, and then we have a box, and we want to refine to the surface of the buildings, and we want to refine everywhere inside a refinement box. OpenFOAM or Snappy Hex Mesh also has the ability to extract feature edges, corners, and stuff like that, and add extra refinement. So that's what this line does. And then you can see here, refinement surfaces are things where we detect intersection of the mesh with the surface and refine on that. We're going to do that on the buildings, and we're going to do it to level 3, meaning that we refine, we split the cell in half, or in half in each direction, so in 8 pieces, 3 times. So the resulting delta X, if you will be refined 3 times. So that means it will be 1/8 of the size it was when we started at the surface. And then we have a refinement region, which means that everywhere inside this box we refine twice. And again, as I said before, it needs to know what is inside and outside of the geometry. So we define a point, an inside point, as 1, 1, 1, and that obviously depends on what your geometry looks like. And the rest is kind of things we don't need to worry about right now. Okay, so we're gonna go ahead and generate the mesh. If I can close this. Okay, so we are back in the OpenFOAM terminal, and to remind you, we just ran the block mesh application, so we created that background mesh. Now we're going to run the Snappy Hex Mesh application, and we're going to add the flag over right at the end. If we don't do that, Snappy Hex Mesh is going to create a new time step for each one of those stages of Snappy Hex Mesh, as we discussed before. So we'll create one with the castellated mesh and one with the snapped mesh. But we don't need that. We can just have it overwrite the condition for the 0 for 0 time. So we'll do that. Oh, right. So there is, as I said, it also contains a function to extract features. Unfortunately, on ACES at the moment, that function is broken. I'm not really sure why. I've tried it on other systems and it works, but unfortunately it is broken. So we're going to have to disable it. So I made a little function to disable it. It's called disable SF, SF for surface features, and this is 10 for OpenFOAM 10. So if you do that, then it should now work to run Snappy Hex Mesh. Okay. So you can see it starts by doing surface refinement, then it does shell refinement, and now it says remove unreachable sections of mesh. That means it's finding out what's inside and outside. And now it's doing the snapping. And I know this is all like flashing by in a millisecond, but we can, once it's finished, we can scroll up a little bit and see what it's doing. Okay, so it's done. So you can see all of these zeros here. that comes up all the time. We love to see those, but that's basically, as I said before, OpenFOAM or Snappy Hex Mesh does continuously monitor the quality of the mesh. So you can see at every single step, every single iteration, every single step that it does in the meshing process, it checks certain quality controls. And you can set these manually in Snappy Hex Mesh Dict or in a separate dictionary or whatever. You can set quality controls for your mesh, but it's you can see here this was a fairly simple meshing task, so we got no errors throughout the entire process, which is kind of rare. Okay, so now we have a mesh. We're gonna now run the solver, and we're gonna, if we look in the control dict, we say that the application that is meant for this tutorial is SimpleFOAM. That doesn't mean you have to run SimpleFOAM. It just means that it's set up for SimpleFOAM. And if you run another solver, you might have some files missing. But you know, you made the mesh and set up the boundary conditions. They should be compatible with a lot of other solvers. But in this case, let's just do what it tells us and run SimpleFOAM. So you can see, if you remember before, we picked the smooth solver, matrix solver for velocity, and we picked the GAMG matrix solver for pressure. So you can see there in every time step that it's telling you that it's using those solvers that we picked. And this is gonna run now. I set the end time to 400 seconds in the control dict. But if you remember, there was also in FV Solutions, there was a residuals control little dictionary there with settings. So if at some point the residuals go below 10 to the -4, it will stop automatically. If it doesn't, it will just continue to 400 seconds, which, spoiler alert, it will, because those residual controls were too strict for this case, I suppose. So while this is running, does everybody, do we have any questions? Anyone got stuck on something? Or are we all good? Okay. I'm gonna say, as we come up on 200 seconds here, you saw that it made a little pause. And that means that it was writing. I didn't say before, but in the control dict, I told it to write to file every 100 seconds or every 100 iterations. So that's why it made a little pause there. I saw that if your Snappy Hex Mesh creates a folder 1 and 2, that means that you didn't put the overwrite flag on it. So it writes it writes a separate instance for each step in the snapping process. And that's not very useful. Well, you can have it that way, but then you have to remember to start from the latest time, which this does by default. So I have a question about opening up the file. Did you mean the instructions document? Yes. So the instructions document, it should have been linked. The course page will have been linked in the same email where you got the Zoom link. And that contains there we go, there it is in the chat as well. And that contains a PDF with basically all the commands that I'm typing at the moment. And the question was about what are we actually simulating? Yes, we're doing a wind around buildings, but you know, that is not my field either. It's just a fairly simple tutorial that doesn't take too long to run, but that uses all of these features like block mesh and snappy hex mesh. This methodology would be the same, depending, irregardless of your application. So don't worry if you're not into wind around buildings. That's just it's just a vessel for us to be able to talk about the different files and commands in OpenFOAM. Okay, so we finished the simulation. As I said, it ran all the way to 400 seconds, which was specified in the control deck that it was supposed to stop at 400 seconds. So we're gonna go ahead and see if we can visualize it. So for that, we need Paraview. So if we can go back to this terminal where we did the load Paraview 11 command, I made another little script that loads this case in OpenFOAM. So Paraview has some built-in loaders for OpenFOAM files. They basically read directly from that file structure that we discussed before. But the kind of interface of Paraview requires a single file to load, like a save file. So basically what you do is you create a dummy empty file. So just so you have something to click on. But I made a little script to do that for you. But again, in the instructions document, you have the instructions for how to do it if you didn't have the script. But I have one called PV11 load case. I'm gonna see if that works. And Paraview throws a bunch of errors, but we don't have to worry too much about those. Okay. Oh, I should, of course, I need to go to that directory first. So we need to go to Scratch, Home, Run, Wind Around Buildings, and then run the load case. Otherwise, it doesn't know what case to load. Okay, there we go. So I don't know if I can make this GUI any bigger, but hopefully it's kind of visible. So when you load Paraview, Paraview has kind of a pipeline browser here on the left, which means you apply things to an object, and that kind of creates a pipe. So you can apply a filter on top of another filter on top of another filter, and you can use that to create your kind of post-processing. So we'll do a little bit of simple post-processing here. First thing I want to do is I want to make sure that it loads in this patch, the buildings that we created. So I'm going to click that, and then I'm going to hit apply. So now we have loaded in something here, but that's the entire mesh, so it's not really super easy to visualize. But I'm going to go ahead and use a filter called extract block if I can. So now I click the extract block filter. It is there under filters, but for some reason I can't click it. I think there's something lying on top here that is invisible to me. That means I can't click it. But anyway, if you click that, you should be able to click the extract block filter. And then we select our patch buildings, and then we hit apply. And there we go. There are our buildings. If we want to look a little bit about Snappy Hex Mesh did, we can change this one to surface with edges. And then we can see that it went ahead and meshed onto that surface. So these buildings were, as we saw before, just imported as a CAD file, and then the mesh was refined and snapped onto that surface. What we're going to do next is we're going to go back to show it as a surface. We want to go ahead and advance the time to the last time step, which is you have the time controls up here. So we'll advance to time 400. You see here, now we're at time 400. And then we want to look at the pressure distribution on the buildings. And you do that by having this extract block highlighted and then click P here. So we can see the wind is coming in here from the left, and we see we have high pressure on this big building here that doesn't have any protection from the wind, and behind we kind of have less pressure. Now we want to look a little bit at velocity. So we want to look from above. So these are camera controls up here. So we can set this one to change the view to straight from above. And if we then select, so now we have this extract block selected. And as I said, Paraview is a pipeline-based software. So anything I do now will be applied to only this building surface. I don't want to do that. I want to operate on the entire mesh so I can see the velocity field. So I click the root, which is wind around buildings, and then I want to make a slice. And I want to make the slice Z normal, meaning vertical, or rather so that the normal is vertical. And we want to do it, say, at a height of 30 meters above the ground. So if I click apply, I get a slice. Now this is still colored by pressure up here, but I can change to be colored by U if that wasn't outside of my what I'm allowed to touch, but I think I can move this a little bit down. There we go. Okay. So there we are. We have a velocity field around these buildings. And that was the end of this tutorial. I think we're going to have a few minutes break. I'm going to see if I can fix this issue that I can't click up here in the top left. Okay, so hopefully that fixed the problem of me not being able to click buttons. I think you guys wouldn't have had that problem. It was just because I was screen sharing that occurred. Okay, so now we completed that tutorial of wind around buildings. Whether or not you're interested in wind around buildings or not, that's a success. But as I said, usually it's very unlikely that you will find a tutorial that does exactly what you want. So we're gonna go in and we're gonna modify this tutorial, which is usually the process you would follow if you set up an OpenFOAM case. You wouldn't start from scratch. You would take something that already exists and that is kind of similar to what you want to do, and you would modify it to suit your needs. And when I say similar, I don't necessarily mean geometrically similar. I mean similar in terms of what kind of methods, what kind of solvers, you know, steady or unsteady, or that you plan to use to work with your case. So geometry is relatively easy to change. All the other stuff is not that easy to change. So we're gonna take this wind around buildings tutorial and we're gonna add another building, and then we're gonna see if we can measure some forces and moments on that new building in this environment. So in order to do that, so I gotta go back to my Scratch foam run directory. I still have this wind around buildings tutorial that we just did. I think it's better if you want to go back to this and look up what we did. I don't want to overwrite that one, so I'm going to make a new one. So I have to, oh yeah. We do copy foam tutorial again, wind around buildings, and then we call it wind around new building. Okay. And then we can do CD to wind around new building. And this is basically a carbon copy of the tutorial that we just ran. I'm going to see if I can make it a little bit bigger so it's easier to see. Okay. Okay, so we still have the same structure of files that we had, but what we wanted to do is add a new building. And as we saw, that the geometry was kind of controlled in the snappy hex mesh dict. So we're going to open that. So NEdit is a graphical text editor that is installed on ACES. So you can use that. If you are more comfortable using any other text editor, please feel free to use this. There's VI. You can also modify the files from the browser, from the file manager in the ACES portal, but then you have to keep flicking back and forth between the tabs. So it's much easier if you can do it like this. So we type NEdit system snappy hex mesh dict. Okay, so we have the geometry here. We have the buildings that are already there. We want to add a new building. We call it new building. We enclose whatever we want to put in brackets. And then OpenFOAM has a bunch of different types of define a bunch of different ways to define geometry. One is, of course, to use a CAD file, but OpenFOAM has some built-in shapes, one of which is a cylinder. So we're just going to make a cylindrical tower for now. We type searchable cylinder, type semicolon. And a searchable cylinder in OpenFOAM is defined by 2 points and a radius. So we type 0.1. Let's say we put it at x equals 150, y equals 30, and it starts, this is the bottom kind of center of the tower. So z equals 0. And then we'll define the top of the tower, 0.2. We put that at the same x and y, so the tower is vertical. But let's make it 225 meters tall. Quite a big tower. Okay, so we have now defined a geometry for this new building. But if I just run it like this, nothing's going to happen because I haven't actually told it how to mesh this one. Okay, so refinement surfaces here, where we have the buildings, we have to add a new building. And we want to, I think, have the same level as the other buildings, level 3.3. So the reason there are two numbers here is there's like a minimum and a maximum. If it has a trouble reaching the quality constraints, it can kind of jump a little bit between these two, but now they are the same, 3 and 3. So that kind of means you're forcing it to be a level 3. We also have to tell OpenFOAM what kind of surface this is we're adding. So we type patch info, type wall. Okay, so now we have our building. One thing I should say, you could also, modify this CAD file that you have here of the buildings to add this new building, and that's probably what you might do if you have a more realistic building than a cylinder. But what you might do then is that creates one patch of all of these buildings. But remember, we want to be able to extract forces on only this building. So it does help to have it as its own separate geometrical object here. So I'm going to save this and close snappy hex mesh dict. One more thing that we want to modify is in the block mesh dict. If I can make this bigger. So we see Z max here is 140 meters. That was good before, but remember this building is going to be 220 meters tall. So that's no good anymore. So I'm going to put it to 300 meters for Z max. And I close that. And then basically we want to add some things in the control deck because I want to be able to measure forces on this building. So I'm going to open the control deck. And at the bottom here, we have something called functions, which is basically functions that will run as the simulation is running in runtime for things like extracting forces, extracting various other things. You can have system commands here so that when it reaches a certain point in the simulation, it calls an external program. You can make it do all sorts of funny stuff. And then in OpenFOAM, that's called function objects. And there's a function object called force coefs that extracts force coefficients. Now the amount of stuff I have to write here to get that to work is a bit much. I'm going to see if I can try to copy it from the training document rather than typing it out. But I closed the training document, so just give me 1 second and I can copy it in. And I can explain what it means once I copied it in. Okay. If it works, okay, it worked. Did I get all of it? Maybe. No, I didn't. Okay, in 1 second. Okay, there we go. I got all of it. And again, don't worry, this is all in the instructions document, so you can copy paste it yourself. So we see we have force coefficients. We load a library called libforces that contains the instructions file to do this. We say write forces every time step, so time interval is 1. We want the patches to get the forces on is new building, which is what we called the new patch. The direction of lift is Z, and the direction of drag is X. And the center of rotation, which it will use to get the moments, is the base of the building, basically. And the pitch axis is the Y. And U infinity is 10, which we saw from the 0/U boundary file. The reference length is 50. That's the diameter of the tower. And the front projected area is 11,250, which is I calculated. So based on this, we should be able to get like CD and moment coefficients from the simulation. So with that, I believe we are done modifying files. We are now ready to run our simulation. But first we have to make the mesh. So again, we create the background mesh with block mesh. We have to, again, disable the surface features because they are broken. Disable SF10. And then we're going to run snappy hex mesh. Overwrite. There you go. Oh, I forgot. I forgot to type the radius of the building. So that we do here. Radius, I think we said 25 meters. Did we check? Yes, radius 25 meters. Okay. Sorry about that. Now it should work.
Björn, if you got a moment as well, you got some questions in the chat.
Yeah, I have a moment now because it's running. Let me see if I can. If you're not able to copy paste with NEdit, it depends. So on the left here, there's a little panel with the clipboard, so you can paste things into this. I am on Google Chrome at the moment, and that should have asked you when you first started the VNC if you will allow it to access your clipboard. If you did that, then you should need this. But if you're not on Google Chrome or another browser that didn't ask you for permission, then you can paste stuff in this clipboard. In order to paste, I cannot use Control V. I used Shift Insert to paste. And I think I tried that in various different browsers, and it works in all of them. So try Shift Insert for pasting. And the question was, are these runs parallelized? Not yet. We'll get to that in like 10 minutes. That will be the next section, but they are very much set up. All the solvers and all the commands I'm using are set up to be parallelized, but they are not used in that way at the moment, but we will get to that. Okay, so we finished our meshing. See, it got a little bit more complicated here. We had an error that it had to do another iteration to resolve, or 2 more iterations to resolve actually. So I guess we made the geometry a little bit more complicated. And now we're ready to run our simple foam to solve this. And now you can see in every time step, it's kind of outputting. I can't really make it stop scrolling, but we'll see once it stops. But you can see that it's outputting in every time step the moment and drag coefficient on the new building. And it's also dumping this to a file, which we're going to look at once it finishes. Any other questions while we wait for this to run? What I added to Snappy Hex Mesh, I added, if you look in the instructions document, there's all the text is in blue is what I added to the different files. I basically added in Snappy Hex Mesh, I added the geometry of a cylinder where I defined it by 2 points and a radius. Oh, sorry, what I forgot, yes, the radius. I added the radius, which I forgot. Okay, I think we're about to finish. Okay, we finished. So you can see here at time 400, which should be the converged situation, we have a moment coefficient of 1.5 and a CD of 0.6. And if we want to kind of look at the history of that, it's saved in a file called post-processing force coefs 1, which is the name we gave it, and then the time we started, which was 0, and then there's a dat file here. So you can see for each one of these 400 iterations, it saved all of these coefficients. Now, if we want, we can see if we can plot these to see what the convergence look like, and we can do that using new plot. So we start new plot by typing new plot, and then we type plot, and then the file, post-processing this file. I hit tab there because there's only one file in there, so you can just hit tab and it will auto-complete the name of the file. So you don't have to type all of that. Then we type using 1 colon 2, which means plot column 1 versus column 2. colon 2 being the moment coefficient here, I believe, and colon 1 being the time step. And we want to use lines. Okay. So that's what it looks like. So we can see here it converged fairly quickly around 40, 48, 50 iterations. We got pretty steady. So that tells me, you know, the residual control that we put before might be too harsh, because it should have stopped somewhere here and been happy. But it didn't. It continued all the way to 400, which was the end time that we specified. But this is a kind of NuPlot is a very good way to just quickly visualize all of these files with numbers, because sometimes they don't make any sense to me just by looking at them. Now we can exit NuPlot. I see in chat that you got core dumped. Can you tell me what step you got core dumped on? And then I can, oh, on block mesh. That is odd. Okay. I am not sure why that might be. Does it say anything in particular what the problem might be, or it just says core dumped? Okay, did you perhaps accidentally type 0 instead of 300 or something like that in the block mesh dict? Because segmentation fault could be a division by 0. Okay, I'll get back to that. See if you can see if if you were able to run the previous tutorial, okay, then I'm sure there was maybe a typo may have caused that. So we finished our simulation, and I want to be able to look at the results. So I'm going to go back into Paraview, which I loaded here in the background. Again, it's slightly annoying to go back and forth between terminals like this, but it's safer in this case to have them loaded in separate terminals. So we're gonna CD to that wind around new building, and we're gonna open that, and then we're gonna do this PV11 load case. You don't need to do this if you don't want to. I'm going to do exactly the same thing as I did for the previous tutorial, but this is more to kind of visualize. One thing I want to mention here, before we wanted to load the buildings, but in this case we want to load the new building as well. And then we're going to do the same thing we did before. We're going to do extract block, and we're going to extract both buildings and new buildings so we can look at them together. And there we go. We made a super obnoxious addition to this city, which is this giant cylindrical tower. And you can kind of see that it's a little bit in the shade or protected from the wind from these buildings here, but most of it is very exposed. So yeah, that was kind of it. It wasn't too bad. We only modified 2 little files, and then we made like a customized simulation. Obviously, in reality, you would need to change quite a bit more, and you wouldn't be so lucky that you found maybe a tutorial of the exact same thing that you want to simulate minus a little cylinder. But I think you get the point that you can quite easily go into these files and add and remove things as you see fit in order to get it to fit your purpose. Okay, so the next thing we want to do is we want to do some parallel processing. That's why we're here on the cluster after all. And that's one of the main strengths of OpenFOAM. So let's go back to the wind around buildings tutorial. So we're gonna go back, wind around buildings. That was the original tutorial that we ran. And we're gonna, OpenFOAM has something called the decompose pardict, which controls how the mesh is decomposed in preparation for running in parallel. Now this tutorial case didn't have a decompose pardict, so we're gonna steal it from another tutorial, and that involves quite a lot of typing. So again, I made a little function to get that decompose pardict, and it's called get dcpd. We'll do that, and now we want to edit that file, which is in system decompose pardict. There we go. So this is obviously stolen from another case, so it won't really it won't be set up for this case. But if you remember when we started the VNC, we asked for 3 cores. So we're gonna decompose the mesh into 3 subdomains. And we're using hierarchical decomposition, and the coefficients for this is here. Basically, this is how many bits it's going to decompose it in each of the cardinal directions, and these obviously have to add up to 3. They don't at the moment, so we're going to change to 3, 1, 1 instead. So that is 3 by 1 by 1. That should give us a decomposition of the mesh. There are a bunch of other options for decomposing the domain here. This is a very simple one. There's Metis and Scotch and other things that you can use. But for this purpose, we'll just use the simple 3 by 1 by 1 division. And we're going to close that. And now we check what's in this. We already have a bunch of files here from the previous run. So I'm going to go ahead and remove them. By this command means remove all the folders that start with 1 through 9, meaning don't remove 0. Which it seems to have done anyway. I'm not sure what happened to 0. So, okay, I think I did that before when I was messing around. I'm gonna recopy that tutorial so I get the 0. Okay. So we're gonna type block mesh. And then we're gonna type get rid of that the features command. So we do disable F10, and then we do snappy hex mesh. Now, snappy hex mesh can run in parallel, so you can generate the block mesh. I don't believe block mesh is parallelized. It might be, I'm not sure. But snappy hex mesh is parallelized, so you can generate the block mesh initially, and then you can run a snappy hex mesh in parallel. If you do that, it takes a little bit longer Obviously, it's faster in real time, but it's going to need to do a lot more iterations to kind of resolve processor boundaries and stuff like that. So I try to avoid that if I don't need to. When I need to would be if the actual mesh in its entirety is more uses more memory than one CPU can handle. But otherwise, I try to mesh in serial because I've had some experience where you mesh the same thing in serial and in parallel it doesn't produce a good mesh. Now we are gonna do decompose par, which is OpenFOAM's way of splitting up the mesh. Okay. So now we can see that we created these directories, processor 0, processor 1, and processor 2, because in the decompose par dict, we said we want 3 different processors. And now we want to run SimpleFOAM, but if we just run SimpleFOAM, it's going to run it as we did before, not in parallel. So we have to use OpenFOAM uses OpenMPI to kind of parallelize. So we type the command MPI run, and we want 3. We want to ask for 3 slots. And then we want to run what command we want to run, which is SimpleFOAM. Now, if I just hit enter here, it's basically going to run SimpleFOAM the same thing 3 times, or the same thing on 3 different processors, which is not what we want. We wanted to use the decomposed domain and run it in parallel. So we have to add the flag parallel. Okay. Now, I believe I saw that when we ran it in serial on 1 core, it took about 180 seconds. In an ideal world, it would take like a third of that if I do this. So we're going to see. It is, in any case, significantly faster to run it on 3 cores. Okay, I'm going to see if I can catch up with any questions. Did you have any luck resolving that segmentation fault that you got? I didn't see any further comments about it. Okay. Well, I mean, if you, as I said, you have all the instructions. So if you start everything clean, I understand that now it's a little bit stressful. You have to type everything quickly as I go through it. But if you go through it by yourself in your own time, I'm sure that you will find out what happened. Okay, so we finished. We finished in 70 seconds, which is a lot faster than we had before. So we are happy that we are able to parallelize like this. And pretty much all commands in OpenFOAM, there are a few like kind of tools, basic tools that are not parallelized, but most things that you will find in OpenFOAM, you can run with the -parallel flag. And as long as you run it together with MPI run to allocate slots, it will parallelize it automatically, and you don't need to worry about it. Same when you are coding in OpenFOAM and writing new applications. All the classes that you will be basing your new application on are already parallelized. So when you write something in OpenFOAM, it's usually already parallelized, and you don't have to worry about it unless you're doing something very advanced. Okay, so we finished the wind around buildings tutorial running in parallel. Now we have about half an hour or so before the course ends. I can either go through the last bit, which is the programming tutorial, or we can have a little Q&A session. I would, my suggestion is maybe if I go through it a little bit quickly, look at the commands we need to run and stuff like that. You don't need to follow along with me, and that way it's a little bit quicker. And then we can leave a little bit of time at the end for a Q&A session, if that's okay. If so, I'm gonna go ahead and see if I can open this file, the instructions, and then I'm not gonna do it in the terminal. I'm gonna just show you what I've written, and we can talk about it. Let's see if I can stop sharing that and share this instead. Okay, so this is the same document that you have. You can see we're here where we ran the parallel tutorial. So the next thing is to modify a solver or modify anything in the OpenFOAM source code, which is honestly one of for me as a researcher, one of the biggest strengths of OpenFOAM is that it's written in a manner that it's fairly easy to implement new methods. It's very well set up to implement new differential equations, partial differential equations, and stuff like that. So I just want to talk quickly through the main steps and kind of pitfalls and stuff like that for doing that. First of all, you want to make somewhere where you will store your new custom applications. I call it foam apps. I put it in my Scratch directory. The next thing, same as with the tutorial cases, usually the way to start writing your own solver or your own library, your own boundary condition or your own turbulence model or whatever, is to copy something that is similar. Because then the 99% of the work is done for you. In this case, I want to make a new incompressible solver that handles transport of a custom field. And I'm going to base it on the IcoFoam, which is the basic incompressible flow solver in OpenFOAM. So basically what I do here is I copy from the OpenFOAM source code, which is stored in this WM project dir environment variable. And I copy this IcoFoam solver and I put it in this directory that I called foam apps. And I call it my IcoFoam instead. Please always rename things when you make a copy of something. Because if you call it the same thing that already exists in OpenFOAM, then there's not going to be perhaps a conflict per se, but you might not know which one you're running. It will depend on what your loading path kind of looks like. So please make sure you call it something unique so you know what you're running. And then same thing here. The source file for this was called icofoam.c. I renamed it to my icofoam.c. That is not as critical because before it's compiled, it's not in the load path. But just so that you have clarity in what you're doing, it's better to rename everything so that you don't accidentally modify the wrong file. The next thing is I put this command here. This is, I would say, the most important command when you're making your own solver. This basically tells it you can go in and do this graphically in this file as well. There's for each library and for each utility in OpenFOAM there is a make folder, and that one has a file called files, and that basically tells OpenFOAM when you compile it what name it's going to give the new thing that you compiled. So I changed it from IcoFoam here to my IcoFoam. So that way, again, I don't have any conflicts. And the same here in the file called files. I changed this variable foam app bin to foam user app bin. This is foam app bin is where all the OpenFOAM applications are stored that you get when you install OpenFOAM. Foam user app bin is where you store your own applications. If you don't change this, and if you don't change this, and you don't change this, you will overwrite the original IcoFoam solver, which is not very good. Now, if usually you have OpenFOAM installed somewhere where you maybe don't have permission to overwrite stuff, but if you do, we will overwrite it if you don't change these two. So what's in this box here is very important that you do first before you do any other messing with the source code. After you've done this, you're kind of safe to start messing around and do whatever changes you want. So as I said, we want to define a new field, a scalar field. It doesn't matter what it is, and we want to create a transport equation for that field. That's what we want the new solver to do. So there's a file called create fields. We want to add this code here that basically defines a new scalar field that we call my field. This basically means that the file name is my field, and this means that it puts it in those folders that we saw before, 0, 1, 2, 3, 4, 5, the time step folders. And we see that it must be read in each time step, and we must also write it, and it automatically writes it at the end of each time step. So when we write our code for this field, we don't have to worry about any of the reading this file from previous runs, that we don't have to worry about writing it. We don't have to worry about where it's stored or anything. We just create it like this, and then it solves it by itself. So let's say we want to create a scalar transport equation for this field. Let's call the field, I call it my field, but that's not really a mathematically simple term to use. So for the purpose of writing an equation, I called it F. So we want to recreate this differential equation here to define what is to happen with our field F in the flow. Now, this might look like it's going to be pretty complicated to implement in OpenFOAM, but the beauty of OpenFOAM and its like kind of toolbox for differential equations is that it's not. So this is the only code here in blue that we need in order to represent that equation. So we already created the variable called my field in create fields. So we see here, we follow the equation here. We take time derivative of my field plus the divergence of my field minus the Laplacian of my field and multiply by new. So that's all there is to it, basically, to represent this equation. I chose to add this code in its separate equation just so that it's easy to see exactly what is what. This can be pasted directly into the source code of my icofoam.c as well, but I created my own file for it just so it's clear. And I put here where to include this file. The grayed out bit here is what you will see if you open this my icofoam.c, the source code of icofoam. And this source code is not going to be, hundreds and thousands of lines long, as you might expect from a whole flow solver, but because it's all modular, it's quite short. So you should be able to find this piece of the code quite easily. And that's where we put our field equation that we just made. We compile using wmake. Just a note here, one thing that I messed up several times is that this is for compiling an executable. If you're compiling a library, the command is wmake libso. And if you don't do that, it's going to throw an error, which is not entirely clear what the error means, but it means that you forgot to tell it to make a library rather than an executable. And here is the some code for testing the new solver. Basically, it's just running the cavity. I don't know if you're familiar, the lid-driven cavity, kind of canonical flow case. Basically, it's a square cavity with flow going on top of it, and the fluid inside the cavity starts circulating as a result. So same as with the tutorials, we create the mesh with block mesh. Because this is a very simple geometry, just a block. We don't need snappy hex mesh, so block mesh is enough. What we don't have is a boundary condition for this field, my field. And we told it that it has to read this field every time. So it will complain if we don't have a file called 0 my field. So I'm just going to copy here the pressure file to my field. And then this is what it looks like when you open this file. And the things in blue are things to modify. So this pressure, when you open the pressure file, it will have a dimension here. If you remember, this vector with, is it 7 elements represents dimensionality. We want this field to be non-dimensional, so we put 0, 0, 0, 0 throughout. And then we set boundary conditions for this moving wall. Moving wall is basically the top opening of the cavity. That's where the flow is going across the cavity. And we want to say that the value of our field there is 1. That's kind of a boundary condition. And everywhere else on the walls, our field should be 0. Those are the boundary conditions that we impose. Now in FV solution, where we define what solvers to use, we need to add a solver to use for. Let me scroll up. When OpenFOAM encounters this code, when it's running, it's going to want to know what schemes and what solvers should I use for DDT, divergence, and Laplacian. So you need to define those in the FV solution first. We say we want preconditioned by conjugate gradient and a lower upper preconditioner. For this field, I just copied this from pressure, I believe. So I didn't sit and come up with this. I copied it from something else, as with everything in OpenFOAM. And then we want to add in the FV schemes, we want to add what kind of divergence scheme for my field. We'll say linear. And then we run this new solver it's now called MyIcoFoam. And if we look at the results in Paraview, we can see that we have, I plotted my field here. It's 1 at the top boundary, as we said, and then it kind of like diffuses a little bit into the domain. So we've successfully implemented a new mathematical equation in OpenFOAM with using very little code. Most of this tutorial was actually just copying files and changing boundary conditions and settings and stuff like that. But the actual code we added was very minimal, which is one of the great strengths of OpenFOAM. So I'm gonna go ahead and stop there, and I'm gonna see if we have any open questions or comments or anything else. We have another like 20 minutes or so. If you want me to go back and show something or anything like that, I'm happy to do so. It is not, the question was, is it necessary to change the control dict for MyIcoFoam? It's not necessary. If you change at the top of IcoFoam, at the top of control dict, it says solver and it says IcoFoam there. If you changed it to MyIcofoam, you'll be able to use OpenFOAM's built-in. OpenFOAM has some built-in run commands that you will see in the all run scripts, for example. And the run commands kind of they run the the executable, but they also at the same time create a log file and do a few other things in addition to just running the executable. And if you want to use those commands, you have to, because those read the control dict. So then you have to change in the control dict to MyIcofoam to make it run the correct solver. But if you're just running it as we did in our tutorial where we run it manually, you don't have to do that. Okay. Yes. So the question is, if you want to add a new type of boundary condition for my field, yes, there's an easy way to do that. It depends what type of boundary condition you want. But if you find one that is similar to what you want to do, this is for my field or for any field really. You copy that one, you give it a new name, you change whatever you want in that source code following the exact same procedure as we did, and then you boundary conditions are selected on runtime, which means that when the simulation starts, OpenFOAM will look through a library of the available ones. And the only thing you have to bear in mind is that your boundary condition that you create will not be loaded by default. So you have to, in the control dict, there is a way to tell it to load a custom library in addition to all the OpenFOAM libraries. But if you remember that, it's basically the same procedure as for compiling a new solver. Make a copy, change the name, change what it does in terms of adding or removing equations or functionality or what have you, and then compiling it. A boundary condition would be a library, so you have to do wmake libso, and then whatever you call that library, be sure to include it in the control dict. In the OpenFOAM user guide, there are examples of this. Exactly what to type in the control dict. I don't have an example up here, but you should be able to find it. But it is easy. It's one extra step compared to what we just did for the actual solver. Okay. So the question is, are there significant differences between the versions managed by OpenFOAM Foundation and ESI, OpenCFD? Would input files be compatible across versions? And the answer is yes and no. Some things are the same. In fact, a lot of things are the same, but certain things, they have a slightly different syntax, and some of the files are called different names. I think, you know, in the beginning, when they first kind of made a fork between those two, there were more differences, but I think they're trying to kind of eliminate some of them so that the files are more portable between them. But no, it's not guaranteed just because you have a case set up in one of the versions that it will automatically run in the other one. As I said, maybe 90% would be the same, but there will be certain things that are called different things, which is annoying. And also some functionality is only available in one of them. I believe that the commercial one has overset grids, for example, whereas the nonprofit one does not. So if you had a case that involved anything to do with that or any other functionality that isn't available, then it wouldn't carry over. So I would, you know, before I start diving into OpenFOAM, I would do a little bit of research, you know, what functionality is available in each of the versions. Usually, you know, unless you're doing something highly specific, it doesn't matter too much. You know, most of the functionality is available in both of them. But then I would pick one and I will try to stick to that one. As I mentioned in the start, I started with OpenFOAM 1.7, and that was like 15 years ago. And I've stuck with that track ever since, because that's what I'm used to. Sometimes I kind of dip into some of the other ones when there's something I want to test out, but for my main kind of my main usage, I would use the one I'm used to, because otherwise I would have to modify a bunch of stuff. That being said, there might be, tutorials in another version that you're interested in, or there might be someone online uploaded a setup for a case you're interested in that is in the wrong version for you. That's fine. Don't be frightened by that. It is possible to run it. You just need to go through a few like kind of trial and error steps. It's going to throw you a lot of errors and say, I don't know what this is, I don't know what this file is, and etc. But it shouldn't be too bad to just change the name of those things and change the syntax slightly to get it to run, because it's, in essence, they are both OpenFOAM. So I hope that makes sense. Any comment from my colleagues at HPRC? Anything I failed to mention about ACES or the login procedure, or anything that could be useful?
I think you hit everything. Maybe just show them the last slide in case they need help.
Yeah, that's what I was gonna do. Yeah. So there is help available. If the question is about OpenFOAM, it's gonna go straight to me, and I'm happy to answer any problems you might have with using OpenFOAM. But I will say, if this is the very first time you're using OpenFOAM, maybe start using it and if you're not familiar with the Linux environment, maybe try starting with the Blue CFD first, just so you can get a kind of a feeling for how it works. And then when you know the basic commands, you can start working on the cluster. That way you don't have to queue in order to test stuff out. Yeah, if there are no more questions, I'm gonna finish. Thanks everyone for attending this course, and I believe that course page with both these slides that you're currently looking at and the instructions document will stay up, and you have the link to that one in the invitation or the email you got earlier today. So you can go in and look at those and kind of in your own time follow all those steps. And yeah, if anything pops up that you don't understand or you need help with, you can reach out.